If you have a cup that's open, some of those molecules that have enough energy to escape will escape, and if it's open, then evaporation happens. What happens is the temperature cools a little bit here because the fastest moving molecules have left. But anyway, over time, this can eventually evaporate. But what happens if you have a sealed container? So this is, you can see here that the molecules escape and they are in the vapor, and then at some point they might be captured back, but there's always a few molecules in the vapor state, and it kind of sets up what's called an equilibrium, where you've got maybe some going back into the liquid, some escaping the liquid, and they're all moving around. This is what's called vapor pressure. So it's a few gas molecules. Even though we're talking about the liquid, there's a few gas molecules that are in the vapor phase above the liquid, and so this builds up what's a partial pressure, meaning a few gas molecules that are due to just the liquid, and this is called the vapor pressure. So the vapor builds up in this space, and it's called the vapor pressure. And we're not boiling yet, we're just at normal temperatures. So here's another picture. Think of this as a sealed container. So the vapor pressure of a liquid is just the partial pressure of the vapor over the liquid measured at equilibrium. And again, we'll talk about equilibrium in a few chapters, but equilibrium just means that, it stays the same. Now, some might go back into the liquid, but some will escape. So we're constantly, the number of escapes and attractions, or what would you call it, escape and grab or attraction, are going to stay constant. So the pressure of the gas in the vapor above the liquid will stay constant, and that's the vapor pressure. So as long as you're at a constant temperature, this equilibrium is set up because, like I said, some molecules can escape, but others are recaptured. That's the word I was looking for, recaptured. So the total number in the vapor stays constant, and that is the vapor pressure. This is just showing, so here you can see this is a barometer, so this is mercury in the barometer. And if you what they're doing here is they're putting some water into the system, and the water is filling up. But notice that, if the mercury column before the experiment was up here, and now the water is in, so you would expect it to move down, the mercury to move down enough to make way for the water, but you can see it's moved down more than what was expected. And you can see if you blow it up that the water molecules in the vapor phase are what is making this filling up this area, and you can actually measure the vapor pressure, because it's what's the difference of what you would expect from the top of the mercury column before the experiment to the bottom. The height of that is the pressure of the vapor. So what are things that affect the vapor pressure? Obviously temperature, because like I said earlier, if you increase the temperature, you increase the number of molecules that have enough energy to escape, and so more molecules, so vapor pressure will increase when you have a higher temperature. So like I said, more molecules have enough energy to escape the surface, and so the vapor pressure increases. And just keep in mind, and we're going to talk about this in just a second, if a compound has a high vapor pressure or a large vapor pressure, this means it will boil at a lower temperature. It's something we call volatile. So it will boil easier if it has a high vapor pressure. And vapor pressure also depends on molecular attraction. So just like the state of attraction, it has to do both with temperature, the state of the phase, the phase that it's in depends on the temperature and also the molecular attraction. So vapor pressure also depends on the molecular attractions. If you have weak attractions, then it's going to be easier for those molecules to escape into the vapor phase, and so your vapor pressure tends to be higher with weaker intermolecular attractions. So weaker attractions, higher vapor pressure, because they can escape each other a little bit easier. So like I said a minute ago, liquids and solids that have relatively high vapor pressures at normal temperatures are considered to be volatile. They have higher vapor pressures. So both of these things are true, and so of course temperature, vapor pressure, if you're talking about the same molecule, will increase with increasing temperature. But when you talk about molecular attraction, so for example, water actually has a pretty low vapor pressure, whereas something like gasoline has a much higher vapor pressure. And you kind of, if you could smell that gasoline evaporate when you pump it into the car. Because gasoline has a smell. But anyway, it does depend on both of these. So it turns out that, and you've probably, if you've boiled water before, you've probably seen this happen where you're watching the boil. This is before it boils. It gets steamy. So that's what's happening is the vapor pressure is increasing with increasing temperature. More of the molecules are moving into the vapor phase. However, it's not boiling yet. But when at the point where the vapor pressure, that's funny, equals the prevailing atmospheric pressure, so the atmospheric pressure surrounding the liquid, that's when boiling happens. So it's when the vapor pressure of the liquid equals the atmospheric pressure surrounding it. Now they're equal and there's nothing holding back the vaporization process, and so it starts to boil. So, if you keep heating as the temperature of the liquid increases, what happens? The vapor pressure increases. Once it reaches to be equal to atmospheric pressure surrounding it, then, like I said, the bubbles will start to form. They'll start to rise out of the liquid, and this is when you're at boiling point. So definitely the definition of a boiling point is the temperature at which the vapor pressure of a liquid equals the prevailing atmospheric pressure, and I'll talk about that in just a minute. So if I say, well, water boils at 100 degrees Celsius, what I'm talking about is the normal boiling point. So we define the normal boiling point as the boiling point where we say the atmospheric pressure is standard, or 1 atmosphere, 760 millimeters of mercury, or 1 atmosphere. So as we'll talk about in a minute, the boiling point can vary depending on what the atmospheric pressure is. So when we have a standard boiling point or a normal boiling point, we're talking about 1 atmosphere pressure. But the atmospheric pressure can vary, so we'll talk about that, like I said. Now, and we'll talk about this also in a little while. During the process of boiling, the temperature will stay constant throughout the whole process. So again, boiling points are directly related to atmospheric pressure. As the pressure decreases, the boiling point of the liquid will also decrease. If pressure increases, the boiling point will increase. So why is that? If the atmospheric pressure decreases, then the vapor pressure will, in order for the vapor pressure to equal the atmospheric pressure, if it's now lower than normal, then it doesn't have to heat it up quite as much to make those equal, and so boiling will happen at a lower temperature. So for example, if you live in Colorado, atmospheric pressure is actually much lower, because if you're at a much higher elevation, the atmosphere gets thinner and thinner. So there's a lower atmospheric pressure higher up in the mountains. And so, for example, in Colorado, it may be only about 0.85 atmospheres. And so the boiling point will then be less than 100 degrees. That's why sometimes you see on boxes, if you're in the mountains or in Colorado, adjust your temperatures and things like that. So food takes longer to cook because it's cooking at a lower temperature. The reverse of that would be a pressure cooker. A pressure cooker will increase the pressure, the atmospheric pressure. It's an artificial atmosphere, but it increases that pressure in the container to much higher pressure. I think maybe 5 atmospheres. I'm not positive, but it will increase the pressure a lot. What does that do? That means that it will take a much higher temperature to get to boiling. And so that means the food will cook much faster because it cooks at a higher temperature. And here's just some examples. So if you're at sea level and the boiling point of water is 100 because you're at your at 1 atmosphere pressure. Abingdon, where we happen to be at slightly higher elevation, our atmospheric pressure tends to be about 0.93 atmospheres, and if we boil water in the lab, which we may do, usually it's about 98 degrees Celsius. And you can see here as you get higher and higher, if you're up in the Andes, the boiling point goes down to 91. If you're up on Mount Everest, the boiling point of water goes down to 76. And a pressure cooker, here is about 2 atmospheres, double the pressure, and it's at about boils at about 120 degrees, so it cooks a little faster. So this slide is showing you the difference of boiling points depending on intermolecular attraction. So boiling point does depend on pressure, and like we talked about on the last slide, that was all the same compound. So depending on the pressure, you could have different boiling points for the same compound, but this is showing that at the same atmospheric pressure, and I don't know why this slideshow has kilopascals, but anyway, 1 atmosphere pressure is this line right here, which is about 101 kilopascals, or 1 atmosphere. And what these lines are showing is the vapor pressure, the vapor pressure at different temperatures. And so at 1 atmosphere, so if the vapor pressure is equal to 1 atmosphere, that's the boiling point, the normal boiling point. So the normal boiling point for ethyl ether is about 37 degrees, 36 degrees. Ethyl ether it actually looks like this. It doesn't have any hydrogen bonding. It has a dipole-dipole interaction. So it is somewhat polar. It's much higher boiling point than, let's say, nitrogen, which would be nonpolar. That would be very, very, very cold temperatures would it vaporize or be liquid. But anyway, ethyl ether, which is kind of a little bit polar, has a low boiling point, whereas ethyl alcohol has a boiling point, looks like maybe 78 or 79. It has hydrogen bonding, so ethyl alcohol looks like this. Oops. Has an OH group, so it has a carbon and an O and an H, so ethyl alcohol is a boiling point. But then water, as we know, H2O, it has much more hydrogen bonding, and so it has a boiling point of 100. Ethylene glycol, which actually is actually this, has 2 OH groups, 1 on each side, is actually even much more very thick. It's like glycerin. Glycerin's not quite the same, but it sort of has that tendency, and you can see that this would kind of come way out here. It would have a much higher boiling point. And so the more hydrogen bonding, the more polar molecules you have, the higher the boiling point. Okay, now when we do convert from a liquid to a gas, it takes energy, and I kind of said earlier that the temperature stays the same, but what we have to do then is pull apart those intermolecular forces. So let's say we had our water, and we've got attractions between water molecules. In order to make it boil, what we have to do, let's use another color, what we have to do is come through here and pull these molecules apart from each other and break those attractions. So that takes extra energy to do that. And that amount of energy that's required to take a liquid to its gas at its boiling point is called the heat of heat of that phase transition. So if we're talking about the heat of vaporization, how much heat is required to boil 1 mole, sorry, my pictures are in your way, to boil 1 mole of any pure substance completely is called the heat of vaporization, or delta H vaporization. So you'll see this little symbol. And that's how much heat is required to boil 1 mole of any pure substance at its boiling point. The opposite will happen. So if you have a gas and you condense it, then the amount of heat that you will be getting back if you condense 1 mole is the opposite. So it's negative. So delta H of vaporization, and then it'll be negative if you're condensing something. For water, so this is the process here. So H2O liquid converting to H2O gas, 1 mole equals 40.66 kilojoules. So that's how much energy. So you would have to put in 40.66 kilojoules to boil the water. And then the reverse, if water vapor condenses, you will release 40.66 kilojoules. So it'd be negative. And of course, every compound will have its own heat of vaporization because it has different intermolecular attractions. All right, so now we're going to switch over and we're going to talk about solids. And so we have a freezing point. The temperature at which a pure liquid changes to a crystalline solid or freezes, of course, is called the freezing point. So the freezing point also does depend on those intermolecular attractions as well, but it doesn't depend so much on vapor, on the atmosphere, the pressure, because the solid liquid transition doesn't really have to do with pressure because there's no gas involved. The melting point is also is obviously another name for the freezing point. So the freezing point is going from liquid to solid, and the melting point is going from solid to liquid, and they should be the same thing. They're identical, and it just depends on which direction you're going. So a lot of times we'll call it the melting point. Like I said, boiling points, unlike boiling points, melting points and freezing points are not really affected by pressure. And what has to happen, again, you have a heat of phase transition. So if we convert a pure solid to a liquid, again, it requires an extra boost of energy to overcome all the intermolecular attractions. And this time they're called lattice energies if it's a solid. And so this is called the heat of fusion, because fusion, if something goes from a liquid to a solid, we can call that fusion. Anyway, the heat to melt one substance is called the heat of fusion, delta H of fusion, delta H fusion. And again, if you're going from a liquid to a solid, then that same amount of energy is released. So it's the opposite. If you're taking solid water and melting it to a liquid, the delta H of fusion is 6.01 kilojoules. So you can see it's different depending on if you're melting or boiling, 6.01 kilojoules. So of course, if you're taking liquid and you're freezing it, you will release 6.01 kilojoules of energy. So just keep in mind, sometimes people get confused by this, but to melt ice is endothermic. You have to put heat in to melt ice. If you freeze liquid water, that is exothermic. It's going to give off heat because you're going from a liquid to a solid. So sometimes it feels like that sounds wrong, but freezing water is exothermic. It has to go to a lower temperature, so it's giving off that heat. All right, so let's look at some examples. So what happens when you put ice cubes in your glass of water? Well, we know that ice cubes melt. Well, what's happening? We need to remember that melting ice is endothermic. You have to put heat in to melt ice. Where's the heat come from? It comes from the water. So the heat from the water is taken out of the water, goes to melt the ice, and now because the heat's taken from the water, the temperature of the water has decreased. So the water has gotten cooler and the ice melts. In a similar way, when we sweat, So the reason why your body sweats is now you have water vapor on your skin, and it takes the heat from your body, and the heat, it's taking the heat from your body and it's evaporating. So you have to put energy in to evaporate the water, and so that's why it feels cooler, because it's actually taking the heat from your skin to evaporate the water, and so it's a way of taking the heat off your body. Okay, this looks really complicated. The Clausius-Clapeyron equation. So there is a relationship between vapor pressure and the temperature. So we saw that earlier. We know in general, if you increase the temperature of a liquid, you increase the vapor pressure. This happens to be the relationship. It's called the Clausius-Clapeyron equation. And you can see here that pressure is directly related to the heat of vaporization. Again, R is our gas law constant, which when we're dealing with gases we use, or when we're using with heat, we use 8.31 joules per mole Kelvin. A is a constant that depends on the identity of the gas. T has to be in Kelvin because R is in Kelvin. And then, so pressure depends on the heat of vaporization. If we take this equation and we actually find the pressure at 2 points, and we take the pressure at 2 temperatures, and we know the delta H of vaporization, everything else is a constant, then we can actually rearrange the equation to use this form of it. So this form of the Clausius-Clapeyron equation uses 2 points of pressure, 2 vapor pressures at 2 different temperatures. So of course P1 is the vapor pressure at T1 and P2 is the vapor pressure at T2. Sometimes this is the way that the delta H is found. So if you know the vapor pressure at 2 different temperatures, you can plug all that in and solve for delta H of vaporization. Or if you know the vapor pressure at a certain temperature and you want to know what is the vapor pressure going to be at another temperature and you know delta H, then you can use this equation. So let's just do an example. Estimate the vapor pressure of water at 85 degrees Celsius. Note that the normal boiling point of water is 100 degrees, so that means the vapor pressure at 100 degrees is 1 atmosphere. And also we're given the heat of vaporization, delta H of vaporization is 40.7 kilojoules per mole. So we're going to use this equation. Notice that, and actually I'm noticing this is the way the book did it, and it's keeping everything in millimeters of mercury. It doesn't matter if you want to use atmospheres, and then your answer would be in atmospheres. It doesn't matter which one you use. So it looks like this example used pressures in millimeters of mercury. So we know that standard boiling point at 100 degrees Celsius, which is 373 degrees Kelvin, so T1 is 373 Kelvin. We know that that's the standard boiling point, normal boiling point, and so the pressure at that point is 760 millimeters of mercury. We want to know what the vapor pressure is at T2, which is 353 Kelvin. So we're looking for P2, the vapor pressure at 85 degrees Celsius, and we're given delta H of vaporization, so that goes in here. We have to be a little bit careful because we had this with our gas laws as well. Notice that the delta H of vaporization is given in kilojoules, but R, we normally give R in terms of 8.31 joules per mole Kelvin. So to get the units to cancel, we convert that to 0.00831 kilojoules per mole Kelvin. So you might only just want to remember it in this form. It's kind of unusual that they give us this form, but maybe because they just don't want the 0.00. Anyway, that's where this 0.00831 comes from, because it's in terms of kilojoules. That's what R is. So you can see here that we plug in the delta H vaporization, we plug in R, those are actually going to cancel. We've got the two temperatures in Kelvin. You want to make sure that they're in Kelvin. You can actually do this math. I would do 1 divided by 373. I would just keep it in decimals. So this would be like 0.00. I would keep a number of significant figures though. 2770. And then this is 1 divided by 358 is 0.002793. So if you take that, it actually equals a negative 0.0000233. And notice that because it's inverse Kelvin. So I plug that number, that's negative. That number is in here, is that. So 40.7 times negative 0.0000233 divided by 0.00831 gives me negative 0.550. So I kind of skipped a step here. So if you keep it this way and you just do all that numbers, you get negative 0.550. Again, 40.7 divided by 0.00831 times negative 0.0000233. So that's what that number is. Gives you negative 0.555. Notice that the Kelvin has canceled and the kilojoules have canceled. Actually, this is kilojoules per mole, so actually the moles have also canceled. So everything's canceled, so this has no units. And now, if you want to undo the natural log, you raise both sides to the e. So we have P2 over 760 equals e to the negative 550. E to the negative 0.550 equals 0.577. So P2 equals 0.577 times 760, or 438 millimeters of mercury. And just keep in mind, you know, if the temperature, if my final temperature was higher, this would be a positive number. This would be a positive number. So this number would be bigger than 1, and so my pressure would increase. So it should make sense that my that because the temperature has gone down, the vapor pressure has also gone down. So anyway, that's kind of a complicated, but it's mostly just like a plug in and calculate your answer.